Hello everyone, welcome to our class, Advanced Thermodynamics and Heat Transfer. Now, let's study Chapter 8, Conduction. We have learned the basic heat transfer, especially conduction. Now, let's directly study Section 1, General Conduction Equation. General Conduction Equation. Consider a three-dimensional solid in which there is uniform internal heat generation and a change of temperature with time. That's to say, the temperature field is T equals T function x, y, z, tau. Tau is time. Tau is time. So, generation conduction equation, we just to build equation to calculate the temperature field, because we have learned the basic heat transfer. So we directly goes into general conduction equation. Here, consider an element at a temperature T at any instant of time. For example, we select an element in a body like this. The position is x, y, z. The time is tau. Certainly, is at any instant of time. Also, we think the element is homogeneous solid, no gas bubble in the body. Let the rate of internal heat generation per unit volume is Q point. We think there is some heat generation. Okay, the density of low is low. The element, the density is low. The specific heat is C specific heat. The thermal conductivity is lambda. We think the element position at x, y, z. So we select this element to consider, to analyze. Okay, here is element like this. Based on the energy balance, we certainly understand the energy flow in the element plus heat generation in the element minus energy flow out from the element finally equals energy increase in the element. So from the energy balance law, we easy to obtain this equation. Just to say, E flow in plus E generation minus E flow out equals delta U. Delta U means the internal energy increase. Okay. For this system, we certainly understand there is 6 surfaces, in, out, 6 surfaces. Okay, for any surface, we calculate the energy goes into or goes out. We understand the total heat flow can be separated to 3 partial heat flow in x, y, z direction. Different direction, there is some heat transfer, heat flow rate. Hence, the heat flow input to the element we can calculate in 3 directions, x, y, z, 3 directions. For example, Qx, capital Qx equals small qx times dy dz. Small qx is the heat flow density. heat flow density. dy dz is the section area. From the Fourier's law, we can calculate the small qx equals minus lambda partial t partial x. This part is the heat flow density times dy dz is the area. Together is capital Qx. Here is in x direction flow into the element. Also in y direction, Qy is small qy dx dz also equals minus lambda partial t partial y dx dz. At the same way, z direction is qz equals qz dx dy also equals minus lambda partial t partial z dx dy. Here dx dy is the section area from z direction, normals z direction. Here is in x, y, z direction. Also, we can calculate flowing out is heat flowing out. Originally, we calculate flow into the body. Also, here we can calculate out from the body. At x and the dx position, we can calculate the heat flow out. Qx plus dx equals Qx and dqx. From the mathematics, we can calculate Qx plus partial Qx partial x dx. From the mathematics, we obtained this part just is dqx. Also, we can calculate equals Qx minus lambda. Lambda is conductivity. Partial t power second, partial x power second, dx dy dz. At the same way, we can calculate at y and dy position, the heat flowing out is Qy plus dy equals Qy minus lambda partial t power second over partial y power second dx dy dz. Also, at z plus dz, we can calculate the heat flow out is Qz plus dz equals Qz minus lambda partial t power second and partial z power second dx dy dz. Here is flow out. We know the heat generation rate is Q point. Also, in unit time, the element will generate the heat Q point times dx dy dz. Because dx dy dz just is the element, the volume. Also, in this time, the internal energy, there is some increase. So increase rho dx dy dz. Dx dy dz just is the volume. Volume times the density, rho is the mass, times Cp. Cp is the capacity. Partial T, partial tau is the change rate. So based on the energy balance equation, we get partial T, partial tau equals lambda over rho Cp times partial T power second over partial x power second plus partial T power second over partial y power second plus partial T power second partial z power second and plus Q point over rho Cp. We can obtain an equation like this. This equation, we can call it is conduction equation. Where we assume lambda, Cp, rho is all of them are constant. For convenience, sometimes we think lambda over rho Cp is a kappa. equals kappa. We can call it thermal diffusivity. Means to express the heat transfer, the conduction rate, fast or low, is not so fast. Maybe kappa is an expression. We know the bigger kappa is, the fast temperature will change. The kappa is bigger, the temperature change fast. So here is a very famous conduction equation. If there is no internal heat source, just to say Q point is 0, so the equation will be more simple, fewer terms. So in this case, partial T partial tau equals lambda over rho Cp times partial T power second partial X power second plus 3 terms. Also, if it is a steady state means partial T partial tau equals 0, no change with the time because it is steady state. So the equation become more simple. Only 3 terms together. Just partial T power second power X power second plus partial T power second over partial Y power second plus partial T power second over partial Z power second equals 0 for steady no generation. So the equation becomes simple. If it is one dimension problem, it only one dimension. So in this case, become more simple. Partial T power second partial X power second equals 0. In this case, partial T over partial X equals constant. So this case, this equation just comes from Fourier's law. Therefore, for one dimension steady state process, the heat flow density small q equals minus lambda partial T partial X equals constant. That's Fourier's law. Okay, let's back to discuss the conduction equation. We can find the conduction equation just like this. The left term, we can call it unsteady state term. Means the internal energy increase, internal energy change. The right term, the first term, means diffusion term. Entering the net heat from three directions. Just is diffusion term. Also, this term is source term, means generation from the body. So in this case, maybe low Cp lambda is not constant. Maybe change with temperature. No problem. But here is this equation is a general equation. Okay, last page we discussed the general equation for conduction. It is in x, y, z coordination. But the general conduction equation in other coordination system also can be used. For example, in cylinder coordination system R, phi, z. In this system, coordinate system, we can do some change, the coordination change. X equals R cosine phi. Y equals R sine phi. Z equals Z. So after changing like this, the general equation can be write like this equation. Also is very long. But every term, the physical meaning is clear. It's not so difficult to understand. It's not so difficult to understand. Here is in cylinder coordination system. Okay, in spheric coordination system, R theta phi. Here is a spheric coordination. In this case, we can do some change, the axis change. X equals R sin theta times cosine phi. Y equals R sin theta sin phi. That is R cosine theta. So after changing like this, the generation conduction equation can be changed like this equation. We can find that this equation is so long, it's very difficult to remember. But every turn, the physical meaning is clear. Okay, thank you very much.